name is Ellen Matson. I am an associate professor of chemistry at the University of Rochester. And so I've been at the University of Rochester for about 8 years. My group studies cluster complexes, specifically these vanadium oxide assemblies that we're using in the context of this work for models of metal oxide surfaces. My co-authors are Eric Schreiber. He is a fifth-year graduate student who's about to graduate and go work for Amy Marie Bartholomew at Yale, brand new faculty member. Great stuff probably coming from her research group. I'm excited for this pairing. And then Bill Bernessel, who is the staff crystallographer at the University of Rochester, who's just a gem of a human and an amazing collaborator in terms of helping us understand these multi-metallic systems and their X-ray structures. Back at the dawn of time when I started my independent career, I really wanted to be different than my PhD and postdoc advisors, so Suzanne Bart and Allison Thau. And this is mainly driven by my respect for their science and the importance that I found in their opinions and guidance. And I figured they'd be much more likely to help me moving forward. They probably would have anyways, but especially if I'm different, like that'll be really cool. So I started looking at these multi-metallic systems. I'd always been fascinated by the idea of metal-metal interactions and how metals can work cooperatively to facilitate some type of multi-electron transformation. And so we started working with these vanadium oxide assemblies pretty quickly, at first from the perspective of trying to understand them as redox active metalloligands. And more recently, we've been focused on understanding them as models for metal oxide surfaces. And that's been really fruitful. Then I was at a meeting, the ICCC meeting in 2018, that was in Sendai, Japan. And my really good friend, Jillian Dempsey, raised her hand at the end of my talk and said, "Ellen, have you ever considered looking at proton-coupled electron transfer chemistry in these systems?" And I thought, no, I hadn't. So we started doing this work during the beginning of the pandemic. We had a lot of time to read, which was really fortunate for my students and I. And my former graduate student, Alex Vertig, Eric Schreiber, the lead author on this manuscript, and I really dug down and began to understand some of the ways that we could measure both the thermodynamics and kinetics pertinent to proton-coupled electron transfer chemistry at the surface of metal oxides, and specifically thinking about how our systems could provide atomic level insight into these types of transformations that usually are quite ambiguous given the lack of, I guess, structural fidelity of extended surfaces. And so that's kind of how we entered into this research space and became so fascinated by these types of kinetically accessible transformations. This ChemSci paper, what was really different is that we were able to modify the structure of our cluster complexes so that we had a single bridging oxide unit. So usually our vanadium oxide clusters, all the bridging oxides that connect individual metal centers are saturated with alkoxide moieties. So we put a methyl group on all those bridging oxides and block any reactivity with protons that we might see in more native metal oxide cluster assemblies. And so in this work, so usually our reactivity is happening at terminal metal oxides. In this work, we have a bridging oxide and a terminal oxide, and we can think now about radioselectivity in terms of metal-oxygen bond activation and where we're protonating and reducing these types of cluster assemblies. And so in higher oxidation states, we see a mess when we add hydrogen atom transfer reagents to our compounds, but when we reduce the compound, we can control the reactivity of the system and really direct hydrogen atom uptake to these bridging oxide sites. The other really interesting thing that came out of this work was that we noticed a really large kinetic isotope effect for hydrogen atom transfer when we were using these reduced forms of our cluster complexes. And to us, this indicated that there might be a different type of mechanism of hydrogen atom transfer, kind of deviating from concerted proton electron transfer to something that might resemble more appropriately an asynchronous pathway. And so this study has really launched us into more mechanistically focused works that'll be the subject of upcoming papers. Yeah, I mean, beyond understanding explicitly the mechanism, which I think is one of the most exciting things that my group is doing right now. And I'm really looking forward to, with our ability to synthetically control the composition of these cluster complexes, is this really neat way that we can integrate cationic or anionic dopants in the assembly. And so I'm really curious about how changing a vanadium to an iron or changing a terminal oxo to a chloro will influence bond association free energies of those either terminal hydroxide groups or bridging hydroxide groups that will then influence the types of small molecule activation reactions. And we really have to do some chemistry now, right? We can hydrogenate quinones, which is great from a polyoxymetallate perspective because it hadn't been seen before with more reducing systems. But now I'm excited to think about how we can start to take chemically or energy poor substrates and convert them to energy rich chemical fuels. You got to figure out how your science fits into this bigger picture. And I think for us, the big motivator is having some type of stakehold in this change in energy economy that we're observing. And so the overall research goals are to think about transitioning to a circular energy economy, and a key step in that is recycling of pollutants, taking things like carbon dioxide and reducing them back down to chemical fuels. I love chemical science for many reasons. One, I'm a member of the editorial advisory board, and so I'm very invested in this journal. I love that articles are open access. I think that it really enhances visibility of research projects to individuals who might not have access. Like my parents don't subscribe to chemical science, but they can download my papers and print them out and put them on their fridge. So that's always really exciting. And the other reason is from an editor match perspective. I think Jim McCusker is just a gem of a human being and really professionally handles manuscripts in a way that give authors great feedback. And even when he's rejecting papers of mine, I feel like I learn a significant amount from the scope of reviewers that are chosen by Jim and other members of the editorial board as well. So it's just one of my favorite journals to publish in. It's definitely my group's favorite journal to publish in. I really hope that this is helpful. I think that everyone should publish in chemical science.